Welcome to my channel. In this video, we are going to discuss thermal expansion in the topic thermal properties of matter. Let me give you some examples which we quite often experience in our day-to-day life. Sometimes sealed bottles with metallic lids which are tightly screwed up, we cannot open them. So to open them, we'll put it in a hot water. So what is the effect? The metallic lid expands, thereby loosening it to unscrew it easily. Mercury in thermometer. We know that there is a liquid mercury in thermometer, and this liquid level of mercury rises when it is put in a hot water. Again, if you take it out, it falls down. Now let us take another example, a balloon inflated. It may expand to full size when it is placed in warm water. Fully inflated balloon starts to shrink when immersed in cold water. That is due to contraction. So what is the observation in all these cases? Substances. In the first case, it is a metal that is solid. In the second case, it is a liquid. And in the third case, it is gas. So substances, I mean, they can be liquid, solid, gas, anything. Substances expand on heating, contract on cooling. A change in temperature causes a change in its dimension. Expand or contract means what? There is a change in dimension. Expand means dimension increases. Contract means dimension decreases. So now let us understand the definition of how do we define thermal expansion. Because I am saying expansion, I use increase. So the increase in dimension, as I said, change can be increase or decrease, but when I am saying expansion, obviously the change is only increase. Therefore, I am specifically mentioning increase. So the increase in dimension of a body or a substance due to increase in its temperature, is called thermal expansion. So this is thermal expansion. So when you heat, so what is happening in those examples? When the temperature is changed, increased, when you heat metallic lid, so there is an expansion, and therefore it has become easy to unscrew it. Similarly, mercury level rises when the temperature rises. Why temperature rises? Because it is kept in hot water. So these examples you are increasing by supplying some heat. So if the increase is along the length, so I call it as length can be along x direction, y direction, z direction, whatever it is, but along only one dimension. So along a particular direction, length. Suppose you take a rod, a metal rod. So this is the length. So that appears to increase in its length by a certain change in length, delta L. So linear expansion. If there is along length, so increase is along the length, it is called linear expansion. Now let us say I have a surface like this. So the increase is along this surface, along this particular surface. So surface or surface area or area I can say. So if the increase, and that is along x direction and y direction, that means it's a two-dimensional one. So it is areal expansion, or you can say surface expansion. Planar, it is planar, along a particular plane, increase along a plane. So that is areal expansion. So this is 1 and this is 2. And the third one is, suppose you consider increase in length thrice, that means along x, along y and along z. That means volume, entire volume. So volume expansion. So this is called volume expansion, or I have just taken a cube, so you can even call it as cubical expansion. So thermal expansion essentially is 3 different types. Number 1, linear expansion along length, and number 2, along area, number 3, along volume. So linear expansion, areal expansion, volume expansion. Now let me define coefficient of these expansions. Coefficient of, let's say first, linear expansion. Coefficient of linear expansion of a substance in the form of a rod, obviously linear along length. So in the form of a rod is defined as change in length per unit change in temperature per unit original length, and is denoted as alpha, I'll explain that. Or you can even say for a small change in temperature delta T, the fractional change in length, I'll write this as delta L by L, is directly proportional to delta T. Now let us try to understand this. If I have this rod, and let me consider the rod length is L1, and after I make it subjected to a temperature change delta T, that means a temperature difference is there, then it appears to increase in its length by delta L, then the final length is L2. So change in length L2 is L1 plus delta L, so that L2 minus L1, I'll write it as delta L, then fractional change is delta L by L. And now this delta L by L is proportional to delta T, and therefore I can write delta L by L, that fractional change, is now equal to, I'll put this alpha t delta t, alpha delta t, where alpha is proportionality constant, that we call it as coefficient of linear expansion, coefficient of linear expansion. Or according to this definition, change in length, so change in length is delta L is L2 minus L1 per unit change in temperature. So delta T is 1 per unit change in delta T is 1 degree per unit original length. What is original length? L1. So per original length. If this is 1 change and this is 1 degree, then this is denoted as alpha. So change in length per change in temperature, unit temperature in unit length, denoted as alpha. So that is what we have written. So from this equation I can write delta L by L into 1 by delta T is equal to alpha. So this is the expression for alpha. Or I can write delta L is what? L2 minus L1. L2 minus L1 by L1 into 1 by, let me put this as T2 minus T1 change is equal to alpha. Then I can write L2 minus L1 is equal to L1 into T2 minus T1 alpha we have here. So alpha. Therefore L2 is equal to, I'll bring this L1 this side, so L1 plus alpha L1 T2 minus T1. So that can be written as the new length L2 can be written as L1 times 1 plus alpha, and this T2 minus T1 I will simply write delta T. So we can write this. So this is another, all these different formulae we can use in solving numericals. So L2 is equal to L1 into 1 plus alpha delta T. Now similarly we can arrive at expressions for areal expansion, coefficient of areal expansion, and that is denoted with letter beta. And on similar definitions, now here change in area, so that is delta A by area, that is fractional change in area, is proportional to delta T. So delta A by A is equal to beta delta T, or I can write beta is equal to delta A by A into 1 by delta T. In terms of area, we can write A2 is equal to A1 into 1 plus beta delta T. So where A2 is the changed area. And now we will write the expression for volume expansion. So the coefficient of volume expansion can be written as gamma. So here it will be delta V, fractional change in volume, that is delta V by V is proportional to the change in temperature. So I can write delta V by V is equal to gamma delta T, or delta V by V times 1 by delta T is equal to gamma, that is coefficient of volume expansion. In terms of the similar expression, I can write V2 changed volume is equal to V1 times 1 plus gamma delta T on similar notes. So this is volume expansion, expression for volume expansion. So depending on how the data is given, either you can use this formula or we can use this formula. And the thermal expansion units, SI units for thermal expansion is per degree Kelvin. See, these are the ratios, delta L by L or delta A by A or delta V by V. So that's a fractional change in length, area or volume, which is dimensionless, then 1 by delta T. So per degree Kelvin or sometimes per degree centigrade. In SI units, per degree Kelvin, or you can write Kelvin inverse, degrees Kelvin inverse or degrees centigrade inverse. So these are the units for thermal expansion coefficients. Now, usually alpha is positive for solids. Alpha is, that means the linear expansion is positive for solids except plastic. As we know, if plastic is heated, so its length decreases. On heating, its length decreases. Its length decreases. So basically these parameters, alpha, beta, gamma, these are the characteristic of a material, and alpha is more for metals as they expand more. Alpha is more for metals, they expand. So for a given material, for example iron, copper will have more linear expansion. So for a given material, it is a characteristic of the material. So it is a characteristic of the material, and copper has more compared to glass. So you can see that it has more linear expansion. Thermal expansion is small for solids and liquids. Thermal expansion is small for solids and liquids compared to gases. Gases expand more compared to solids and liquids. Therefore, thermal expansion is small for solids and liquids compared to gases. And more about gases we will learn in another chapter, kinetic theory of gases. Now, let us see what is the relationship between these three coefficients, alpha is to beta is to gamma, and that comes out to be 1 is to 2 is to 3. So, let us see how we get that. There are two ways that we can do, and the simplest way is, let's say delta L is equal to, or we have this relation delta L by L is equal to alpha delta T. So I'll write delta L is equal to L alpha delta T. So if I write delta V, then I can write L plus delta L, change due to the change. So L plus delta L, now I'll write L plus delta L whole cube minus L cube. So volume is L cube. Therefore, L plus delta L whole cube minus L cube, which means I am writing L2 cube minus L1 cube, where L2 is L plus delta L, L1 is normal L. So this when we expand, so delta V is equal to 3L square delta L I get. How do I get 3L square delta L? Neglecting when you expand a cube plus b cube, a plus b whole cube, then you will have delta L square term, delta L cube term. Delta L being very small, we can neglect delta L square term, delta L cube term. So you remain with this term. So delta L cube. So now this I can write it as delta V, I can write it as 3 and then this L cube by L square I can write, I am just rearranging the term, L square, L cube by L, delta L. So L cube is nothing but volume. So I can write this as 3V delta L by L. So I will take this delta V here. So delta V by V is equal to 3 times V, V I have taken here, 3 times delta L by L. So that is 3 times delta L by L is what? Alpha delta T. Alpha delta T. So now I will write delta V by V and I will bring this delta T here. So 1 by delta T is equal to 3 alpha. 3 alpha. So what is delta V by V into 1 by delta T? It is nothing but gamma. So gamma is equal to 3 alpha. Similarly, we can prove beta is equal to 2 alpha. Therefore, alpha plus beta plus gamma is equal to alpha is to beta is 2 alpha, gamma is 3 alpha. Therefore, that comes out to be 1 is to 2 is to 3. So this is how you can arrive at relation between the 3 parameters. And now we know that beta is equal to 2 alpha, therefore alpha is equal to beta by 2 and gamma is equal to 3 alpha, and now I will write 3 times alpha from here, so 3 times beta by 2, therefore gamma is equal to 3 beta by 2. We can solve problems depending on if gamma is given and you are asked to calculate beta, so you can directly take this relationship, or alpha is given, you are asked to calculate beta, so you can take this relationship. So this is about the thermal expansion and coefficients of thermal expansion, which is an important topic in this chapter. So I will come with another important topic in my next video. Until then, keep watching, keep learning. Thank you.